Have you ever wondered how a Formula One car seems to be literally glued to the track? Or how surgeons can predict blood flow in a patient's heart before they even make an incision? Well, the answer lies in a technology that has completely and quietly changed our world. It's called Computational Fluid Dynamics, or CFD for short, and it gives us the incredible power to see the invisible. So, let's get right into it.
All right, so let's jump right in. To really get a feel for just how powerful this stuff is, I want you to picture one of the most high-stakes engineering challenges you can possibly imagine.
Think about this, a space shuttle blazing back into the atmosphere. The heat, the airflow, it's just unbelievably intense. And you can simulate all of that before a single piece of metal is ever cut. I mean, this isn't science fiction, right? This is the kind of life or death problem CFD was built to solve. It's like having a perfect virtual wind tunnel, a digital playground where you can test the most extreme conditions without risking, hardware or lives.
Okay, so that's a pretty mind-blowing example of what CFD can do. But what actually is it? How does it all work? Let's get down to the basics.
All right, so here's the formal textbook definition. It's a bit of a mouthful, right? But really, all it means is we're using computers to figure out how fluids are going to move and react. And remember, when we say fluids, we're talking about pretty much anything that flows, so liquids and gases. It's about predicting their behavior in, well, basically any situation you can dream up. I really like this way of thinking about it. It boils down all that complexity. At its very core, CFD is the art of taking these super complex laws of physics, the ones that govern how things flow, and turning them into something a computer can actually chew on. And what's that? It's numbers. We're talking mountains of numbers, billions and billions of them.
And the rules that all of this is based on? They're called the Navier-Stokes Equations. Think of them as the fundamental rulebook for how every fluid in the universe behaves. The problem is, these equations are just ridiculously complex. For a long, long time, they were basically unsolvable by humans. That's where high-speed computers come in. We feed these equations into the machine, and it does the heavy lifting, crunching all those numbers. It's no surprise, then, that the story of CFD really is the story of the supercomputer. One couldn't exist without the other.
So, suddenly having the power to solve these equations, it was a total game changer. It wasn't just a small step forward, it was like we discovered a whole new dimension for science and engineering. It fundamentally changed how we even think about fluid dynamics.
For hundreds of years, if you wanted to understand how fluids work, you really only had two tools in your toolbox. On one hand, you had pure theory, pen and paper math. But to make the math work, you often had to simplify things. On the other hand, you had pure experiment. You'd build a physical model, stick it in a wind tunnel, and see what happens. Both are super important, but then CFD came along. It became this incredible third dimension that sits right between theory and experiment, connecting them in a way that was never possible before. So what makes this third dimension so powerful? Well, for starters, you can simulate things that would be way too dangerous or just flat out impossible to test in the real world. Think about an explosion, or maybe a critical failure inside a power plant. You can't just do that, but in a simulation, you can. You can peek inside and see all the hidden details of the flow. You can test 20, 50, 100 different designs in the time it would take to build just one physical prototype. And of course, it's way, way cheaper.
And that's because CFD isn't just one thing. It's this amazing meeting point for a whole bunch of different fields. You've got the fundamental laws of physics. You've got the mathematics to describe those laws. Then you need the computer science to actually solve the equations. And the whole reason we're doing it is for engineering, to build better stuff. But then there's this final crucial piece, visualization. Because you can have billions of data points, but they're useless until you can turn them into an image, something our brains can actually wrap around. Now, this didn't just happen overnight. This incredible tool has been developing for decades. The history of CFD is really inseparable from the history of computers. You can see the first glimmers of it back in the 40s, but things didn't really kick into high gear until the 1970s, when mainframe computers gave us the horsepower we needed. Then, in the 90s, when high-performance computing became affordable, well, that's when CFD just exploded. It went from being a niche tool for aerospace to something used in just about every industry you can think of. And I'm not exaggerating when I say it's everywhere. The applications are just mind-bogglingly diverse. We're talking about everything from designing massive airplanes all the way down to studying the flow of blood in the tiniest human artery. The range is just incredible, and some of the uses are things you would never, ever expect. Okay, just look at this list. It's everywhere. We use it for the aerodynamics of cars and planes, sure, but also for the hydrodynamics of ships to make them more efficient. We use it to perfect combustion inside an engine and to figure out how to cool the tiny microchips in your phone. It helps architects design skyscrapers that can withstand high winds and helps city planners track how pollution might spread. And then there's medicine, where it's literally helping us understand the flow of blood in our own bodies. It's just wild.
Okay, let's zoom in on a really specific modern example. We're looking at a simulation of a lithium-ion battery, the kind that's in your phone or in an electric car. Using CFD, engineers can actually see the heat building up and watch the chemical reactions happening inside. And that's absolutely critical for making these batteries safer and making them last longer.
All right, but if you want a really surprising one, check this out. People have actually used CFD to model the inside of an igloo. I mean, how cool is that? They can simulate how the body heat of the people inside, and maybe a small lamp, creates these air currents that keep the space livable, even when it's 30 below zero outside. It's this perfect marriage of ancient, brilliant design and super high-tech analysis.
So, okay, after hearing about everything from space shuttles to igloos, you might be thinking, wow, CFD is a done deal. They figured it all out. But that's not quite right. The truth is, the field is still evolving. The future is very much, well, fluid.
It's incredibly powerful, for sure, but CFD isn't what you'd call a mature technology yet. I like to think of it as a giant, complex puzzle, and we're still finding and fitting some of the really tricky pieces. Researchers all over the world are pushing the limits every single day, because there are still some major challenges we need to crack.
So what are these big challenges? Well, one of the holy grails is turbulence. You know that chaotic, swirling motion you see in a campfire smoke or in the rapids of a river? That's turbulence. And modeling it perfectly is just insanely difficult. Its randomness takes a staggering amount of computer power. The same goes for getting things like combustion and complex heat transfer exactly right. So a huge part of the research today is just about finding better, faster, more efficient ways to get reliable answers.
When you boil it all down, CFD is this incredible tool for making the invisible visible. It lets us see this hidden dance of fluids that's happening all around us, all the time, shaping everything from the smallest cell to the largest galaxy. And as our computers get more and more powerful, the possibilities just keep expanding. Which leaves us with a pretty exciting question to think about, right? With this power to see almost anything, what will we choose to see next?